just have your luggage ready. In fact, don't necessarily have to check out, but be ready because we're going to go from here to eat lunch and then we're going. Okay, so I would like to introduce Janko Stennder from, I got that so wrong, Stennder from, well, I'm not saying that, from Germany. Sorry, he's going to speak to us about algebraic structures in pre-Riesz spaces. So, yeah, take it away.
Okay, thanks a lot for the introduction. I hope everyone can hear me well. First of all, thanks a lot to the organizing committee for the whole conference. I've been enjoying it a lot, and yes, I'm really sad that I couldn't be there in person. Sadly, I've got some minor heart problems which prevent me from coming to Tunisia, but I'm still happy that I can present my PhD topic to you online. And part of my PhD thesis is about the algebraic structures in pre-Riesz spaces. And as Anke's PhD student, I follow the last two talks by leaving the familiar setting of vector lattices and yes, trying to get results we have in vector lattices also for partially ordered vector spaces. And I want to focus on algebraic structures. So I think I want to motivate my topic with presenting you some things you know from vector lattice theory, and especially lattice ordered algebras. So we want to call some vector lattice A or some vector space A in L algebra if it's a vector lattice with some associative multiplication such that the product of two positive elements is always positive as well. And there are some special kinds of lattice ordered algebras. I think most of you will know them. For example, the well studied and probably the lattice ordered algebra with the richest theory are the F algebras, where if we have two positive disjoint elements, then if we multiply by the from the left or from the right by some other positive element, then they're still disjoint. And some two other kinds of lattice ordered algebras. For once, the D algebras, which satisfy that any supremum is preserved by multiplication by positive elements from the left or from the right. And we have the almost F algebras, where just if we have two positive disjoint elements, then the product also has to be 0. And as is shown in this scheme, we have that every F algebra is always a D algebra and always an almost F algebra. But the notions of D algebra and almost F algebra are in general not related. And I was first introduced to this whole field in the positivity when I was studying the tensor product of almost F algebras together with Anke and Damla. And there we kind of were introduced to this topic and realized that all those multiplications are just given by special kinds of bilinear maps, which are shown here. So in F algebras, you just have that the multiplication are bi-orthomorphisms. In D algebras, those are Riesz bimorphisms, and in almost F algebras, those multiplications are orthosymmetric. And as Anke and Onno told you before, we now have like a richer structure in partially ordered vector spaces as well, which the structures were introduced in the last decades, starting by Van Hande, and then Anke and Onno did a lot of work. And all those notions we have here, we can now as well define in partially ordered vector spaces. So that was my starting point for my PhD thesis, to see or to study those kind of bilinear maps or generalizations of those kind of bilinear maps to partially ordered vector spaces. And I mean, there are not going to be a lot of surprising results in my talk now, but I will show that even in the case of partially ordered vector spaces, a lot of results we know from the theory of FD or almost F algebras can still be true in partially ordered vector spaces. And I want to begin by defining those kind of algebras. And we begin with an ordered algebra, which is just some partially ordered vector space with associative multiplication, such that the product of positive elements is again positive. And Anke showed you how we can define disjointness in partially ordered vector spaces, which was some equality of sets of upper bounds. I don't want to show you the details again, but we know that we have this disjointness there, and then we can define some ordered algebra to be in so-called OF algebra if it satisfies the same properties as in the vector lattice case, only now with the disjointness in partially ordered vector spaces. And I'm not like 100% happy with the name of those kind of algebras. If you have any better suggestion on how we can call those algebras, I'm open for any suggestion. But for now, we just put an O in front, and then we know that we are in the partially ordered vector space case. And for almost order OF algebras, we can do the same thing. We just take the definition from the vector lattice case and write it down exactly the same. Now the question is, what can we do for an OD algebra? Because to get the supremum in kind of order upper bound notation is not really clear, but I'll show you that there are already generalizations of Riesz homomorphisms to partially ordered vector spaces, which I will define later and also show some basic properties. But I want to begin to show some first results for the OF algebras. But first we note the thing that Anke already told you earlier, that being an OF algebra is in partially ordered vector spaces a much weaker condition than in vector lattices, because there might be very few or even no non-trivial pairs of positive disjoint elements. Those were the anti-lattices or disjointless-free spaces Anke was talking about earlier. And we can have a look at this example here. If we take the space of all polynomials on the interval 0 to 1, then there are no non-trivial disjoint pairs of elements. Anke already told you earlier that the disjointness here is the same as in the continuous functions. So just pointwise, the supports have to be disjoint. So the space is actually disjointless free. And then we know that any O algebra multiplication on this space is already an OF algebra multiplication, because disjointness is, any bilinear map is basically in bi-orthomorphism. So we can, for example, consider the multiplication given here, where we just take the product at any point is just with two polynomials is just P1 at 0 multiplied by P2 at t. And then we see that this multiplication is not even commutative, but any multiplication is an OF algebra multiplication. So we already have a counterexample for a very famous result in F algebra theory, namely that every Archimedean F algebra is always commutative, but we see that in general this cannot be true in partially ordered vector spaces, because disjointness is just such a weak notion in partially ordered vector spaces. And one could assume that something like pervasiveness, Anke also talked about this earlier, which are just, which have kind of enough or more disjoint elements, but this is still not enough. But we could find in the special case of spaces of continuous functions, could find a condition which kind of ensures that there are enough disjoint elements. And this property we called SD, which kind of means like separation by disjoint elements. So we have some non-empty compact house of space K and take some subspace of CK, so the continuous functions on K, and then this subspace has the property SD if for every two distinct points in K we find two positive disjoint elements in X, such that x1 of t1 and x2 of t2 are bigger than 0. So if you have two distinct points, we can always separate them by positive disjoint elements. And yeah, some easy examples to get a feeling for this property. Every CK space for any k on an interval has ST. But for example, the Namioka space, which are just continuous functions on -1 to 1, where evaluated at 0 is just the average of the evaluations at -1 and 1. This space does not have the property SD, but it is pervasive. So it kind of has a lot of disjoint elements, but still doesn't satisfy this property SD. And this property SD will play a huge role in many of my results concerning OF algebras and almost OF algebras. And I want to begin by showing some representation theorems on CK spaces. First, we have the result for the vector lattice case, already shown by Conrad in 1974, where if we have some associative multiplication in C of k, then this multiplication is an F algebra multiplication if we have some positive weight function, and we can write the product of F and G as such a weighted multiplication, or so the weighted standard multiplication. So this is already long known, and I could generalize this result by replacing the C of k by any order dense subspace of C of k with this property SD. So the order denseness here again means the one Anke and Onno explained to you. So the one where any function here in C of k can be written as the infimum of all the elements of x which lie above the function here. So this multiplication, or if we have a multiplication here in x, then it's an OF algebra if we get basically the same representation. So already some similarities between the partially ordered vector space and vector lattice case. And the second result concerning OF algebras I want to show you is about Markov operators. We quickly recall what a Markov operator is. If we have two ordered algebras, x and y, with units, and here I mean multiplicative units, and the set of Markov operators is just a set of all positive operators which map the unit of x to the unit of y. And then we know, or it was proved by Van Putten in 1980, that if we have two Archimedean F algebras A and B with unit elements and some Markov operator, then we have the following equivalence, that T is an extreme point in the Markov operators, if and only if it's an algebra homomorphism, and if and only if that's a Riesz homomorphism. And yeah, basically all the notions here are also available in partially ordered vector spaces. So was the question if the same holds in this case, and at least in the, again, order dense subspace case of C of k, I could prove basically the same result. So in this case, we have order dense subalgebras of two different C of k, so C of k1 and C of k2, and they are equipped with any F algebra multiplication, and the units are also in the subalgebras. So E1 is an X and E2 in Y, and my space X also has to satisfy this property SD. Then we basically get the same equivalence, only that instead of Riesz homomorphism, we have Riesz star homomorphism here. And the Riesz star homomorphism is one of the generalizations I'm going to tell you about in a few slides. But I just want to remark one little thing. Namely, we have here, or I want X to satisfy SD here, but there's nothing about disjointness in this theorem. So the question is, why do we need SD? But the problem is that in general, an algebra homomorphism is only a disjointness preserving operator. So if it's a positive algebra homomorphism, then of course it's a positive disjointness preserving operator. And in the vector lattice case, it's the same as a Riesz homomorphism, but in partially ordered vector spaces, this is in general not true. So we need the property SD to again ensure that the disjointness actually means something. And then using a result Anke, Onno, and I had in a recent paper that any positive disjointness preserving operators actually re-star, we can then finish the theorem. So SD is kind of hidden here as algebra homomorphisms relate more to disjointness than to actually to Riesz homomorphism, although in vector lattice, of course, it's the same. Okay, a quick look at our scheme. We have the OF algebras covered for now, all the results I wanted to show you. Now I want to fill in the question mark below the OD algebra. So basically show you what I meant with this Riesz-star homomorphism on the slide before. So if I have two directed partially ordered vector spaces X and Y and some linear map from X to Y, then Van Handel introduced the notion of a Riesz-star homomorphism, which just satisfies this inclusion for every non-empty finite subset f of x, and this upper u, or the u and the l in the exponent, again denote here the upper bounds of some set, and l the lower bounds of some set. So the f u l is just set of all lower bounds of all the upper bounds of f. So it's not really a definition which you want to work with. It's kind of complicated, but I'll show you a very much nicer characterization of Riesz-star homomorphisms when we switch to the setting of pre-Riesz spaces. And one could also ask why we need a finite subset f here and not only two elements, as we have for a Riesz homomorphism in a vector lattice. We just have the supremum of two elements. Why can't we just use a set which contains two elements here? This actually Van Handel had in his thesis. There was his original definition, but Anke and Onno found a mistake in his proof. And actually only with this definition, we get a nice characterization I'm going to show you in a few slides. And it's still open if two elements are enough. So that's an open question if we can substitute a finite subset f here with a two, or a set with two elements in this definition. And there's also a second generalization of Riesz homomorphisms, which is also called Riesz homomorphism, defined by Duskes and Van Roy in 1993 as well. And this is also an equality of sets where upper and lower bounds are involved. And just note that every Riesz homomorphism is always a Riesz-star homomorphism, but not the other way around. And of course, if x and y are vector lattices, then those two notions coincide with the Riesz homomorphism in the vector lattice case. Otherwise, they wouldn't be really good generalizations. And I promised you a nice characterization of those Riesz-star homomorphisms. And this is only true in pre-Riesz spaces. And today you heard like the third times of pre-Riesz spaces, but I'll quickly show you again what a pre-Riesz space is. It's just some partially ordered vector space where we find a Riesz space or a vector lattice y and a bipositive linear map from x to y such that the image here is order dense in y, where we again mean the order denseness in the partially ordered vector space sense. And this is also equivalent that we find some Riesz space and a bipositive linear map such that the range is order dense, and this range, the image, and the image generates y as a Riesz space. So every element in y can be written as a difference of finite suprema of elements from the image. So this, you already heard this twice, so I don't want to talk too much about it. Just note that the Riesz spaces, as in 3, are all isomorphic. And the ones from 2 we call vector lattice cover of x, and the ones from 3 we call the Riesz completion of x. And we denote this Riesz completion by x rho in general. So again, the nice thing about pre-Riesz space is that they can be embedded in a vector lattice in a very good way. Okay, now the characterization of the Riesz-star homomorphisms also obtained by Van Haande. If we have two pre-Riesz spaces with their Riesz completions and some linear map between the pre-Riesz spaces, then this map is a Riesz-star homomorphism if and only if there exists a Riesz homomorphism on the Riesz completions, such that, yeah, this Riesz homomorphism extends T in a sense that kind of commutes with embeddings in the Riesz completions. And this Riesz homomorphism is also unique. So Riesz-star homomorphisms are exactly those linear maps between the pre-Riesz spaces which extend to Riesz homomorphisms on the Riesz completions. And the difference to Riesz homomorphisms here are, of course, they also extend to Riesz homomorphisms on the Riesz completions, but not every restriction of a Riesz homomorphism is always a Riesz homomorphism on the pre-Riesz spaces. Yeah, it's kind of confusing because the notions have the same name, but yeah, Riesz-star homomorphisms are kind of the right generalization for the case, for the setting of pre-Riesz spaces. And yeah, as we are concerned with multiplications, we can now consider the bilinear case of those kind of maps. So we have some Archimedean pre-Riesz space with Riesz completion x row, and now a bilinear map from the Cartesian product of x with x to x. And I proved that if x satisfies some mild technical condition, which we call just P now, and the map is a Riesz-star biomorphism, or if the map T is just a Riesz biomorphism, then T has a Riesz biomorphism extension to X row. So we basically have the same theorem as in the linear case, only that for Riesz-star biomorphisms, we need this condition P. And yeah, I'm working on this condition. It's kind of, yeah, it's eluding me to find a counterexample for a pre-Riesz space which does not have this property. Right now, every pre-Riesz space I know satisfies this property, and I can't find one which doesn't. So every pervasive space, every space with Riesz decomposition property, and also every order unit space satisfies this property, but I can't find one which that does not satisfy this property. So almost every space I know, yeah, satisfies this property. So now we have the right notions at hand to define an OD algebra or an OD star algebra, where the multiplication is just a Riesz biomorphism or a Riesz-star biomorphism. So we have one more algebra in the partially odd vector space case, basically. And from the extension theorem I just showed you, we can already get an easy corollary, namely that if X is an Archimedean pre-Riesz OD algebra or an Archimedean pre-Riesz OD star algebra with this property P, then the multiplication can be extended to a D algebra multiplication in the Riesz completion. So we can see our pre-Riesz space as a subalgebra of our Riesz completion already. And conversely, every order dense subalgebra of a D algebra is already a pre-Riesz OD star algebra, because the restriction again is only a Riesz-star homomorphism. So we only get that the subalgebras are a pre-Riesz OD star algebra. And again, I want to start with representations on CK spaces. Boulabia proved in 2004 that an associative multiplication on a CK space is a D algebra if and only if we find such a weight function and two maps from K to K, such that we can write the product as such a weighted composition multiplication. This is already known. And I could prove again the same thing in order dense subspace of CK. When X is an OD star algebra, then we always get such a representation as well. So the representations on CK work really well so far. But I want to have some results which are not in CK spaces. And first, I want to show you again the lattice case. But maybe we should discuss notation a bit. We have some Archimedean D algebra A, then the set of nilpotent elements NA, which are just elements such that there exists an exponent, such that A to this exponent is 0, is denoted by NA. And it's called semi-prime if 0 is the only nilpotent element. Then it is well known that in an Archimedean D algebra, the set of the nilpotent elements are just the ones where the cube is 0. And this set of nilpotent elements is an order ideal and of course also a ring ideal. If an Archimedean D algebra has a multiplicative unit, a positive multiplicative unit, then this is already a weak order unit in A. And in this case, our Archimedean D algebra is already a semi-prime F algebra. And if A is semi-prime, then A is an F algebra. So those are the few results we have or we know about D algebras, and I tried to get the same results for OD algebras as well. So we have an Archimedean pre-Riesz. We always need the pre-Riesz OD algebra with a Riesz completion X row. And instead of OD algebra, I could also write OD star algebra with this property P, but I just write OD algebra here for brevity. And yes, I could prove that the set of nilpotent elements is basically given in the same way. And it is a solvex order idea and a ring idea where solvex is the generalization of solid and convex, or a combination of it. And order idea, of course, is here meant in the partial order vector space case or setting. Yes, if this Archimedean pre-Riesz OD algebra has a multiplicative unit, then this is also a weak order unit. And I of E, so in the Riesz completion, is then also a unit there. Therefore, our Riesz completion X row becomes a semi-prime F algebra with unit I of E, because the result I just showed you. And then as X is just a subalgebra of the Riesz completion, it is already an OF algebra as well. So we get the same result here. And if our space X is in addition pervasive, then we get that our pre-Riesz space is semi-prime if and only if the Riesz completion is semi-prime. And in this case, then also X row becomes a semi-prime F algebra, and therefore X is also an OF algebra. So we get basically the same results in the partially ordered vector space case, as long as we have a pre-Riesz space. Okay. We filled out all the question marks, and we know at least that when we have SD in some subspace of continuous functions, then we have the implication as in the vector in this case. Otherwise, this implication here does not hold in general, as I showed you before. And I have like 2 minutes left, so I want to quickly show you a few things about almost all F algebras. We again begin with a representation on C of K spaces. There, Sheffield proved 1981 that an associative multiplication on CK is an almost F algebra multiplication when there exists a family of positive measures indexed by the compact set, such that in every point evaluated, the product is just given by this integral with respect to the measure. So this is also already known. And then I tried to prove the same thing in partially ordered vector space, so an ordered in subspace of C of K. But in this case, we in addition need the Riesz decomposition property. Of course, we need SD again, because otherwise disjointness doesn't really mean anything. But if we in addition assume RDP, we get basically the same representation as in the vector lattice case. And the RDP here is needed because we needed some extension result for positive bilinear map. I mean, the multiplication is just a positive bilinear map. We wanted to extend it, use integral representation there, and then SD to get this specific representation. But of course, we don't have an easy extension theorem for positive bilinear maps. And the only thing I was able to prove is with RDP some kind of Han-Banach result, or similar to it for the bilinear case. So I don't really know if RDP is necessary here or not. This was just the only thing I could manage. Yes, and then I want to close with link between OD algebras and almost OF algebras. Because in a vector lattice case, Bernau and Hausmanns proved that an Archimedean D algebra is an almost F algebra if and only if it has positive squares, if and only if it's commutative. So every commutative Archimedean D algebra is always an almost F algebra. But of course, we know in general this will be not true in partial vector spaces because of the disjointness problem. But we at least get that an Archimedean OD algebra is an almost F algebra when every positive disjoint elements commute. But because of the few disjoint elements, maybe this is a very weak statement. And we can, for this, we can again consider the multiplication I gave you in the beginning. Because of the representation theorems, we know that this is an Archimedean OD algebra. And because disjointness is because it's disjointness free, this is also an almost OF algebra. But yeah, the space is not commutative and also doesn't have positive squares. So the result from Bernau and Hausmanns is in general not true. But if we consider order dense OD algebras of CK spaces, again, which satisfy this property SD, then we get the same equivalence as in the Bernau-Hausmanns theorem, that it is an almost OF algebra if and only if it has positive squares or is commutative. So that's basically everything I wanted to tell you about those generalizations of the different kind of lattice ordered algebras. And you can imagine that there are thousands of other questions one can ask now, because every result in FD or almost F algebras might or might not be true in the partial ordered vector space setting. And as Anke said, you're dearly invited to join my quest to understand those algebras. Thanks a lot.
Oh, Janko, thanks. That was nice. Sorry. Where is the? Are we ready? Okay. Janko, do you hear us?
Yes.
Okay, all right, thank you. You did say that we've now seen the definition of this pre-Riesz space 3 times. and Anke kept on saying it's a playground, and you say order dense in your setting. And I feel sorry for you. Your playground is the jungle gyms upside down. Okay, but does anyone here have a question for Janko? Yes, you do.
Thank you for an interesting talk. So in page 15, you consider bilinear maps from X cross X into X. And I was wondering, which I think is a natural question, what happens if you consider maps from X cross Y into Z? And the reason that I'm asking is because it might show you also which property you need in the range spaces and which property you need in the domain spaces. So if you looked at...
Yeah, actually, I prepared the talk only for the algebra case, but in general, I considered multilinear maps on different pre-Riesz spaces. So I usually had spaces x1 to xn into some space y and considered it in there. So I just focused here on algebra multiplication stuff.
Okay, so in which condition do you need on one of the xn's and which on y?
On Y, I don't need any. No, on every space, I need this condition P actually.
Ah, okay. Thank you.
Yes, or on every, I mean, yeah.
Okay, thank you. Anyone else?
Thank you for the talk. I have two questions. The first is the connection between algebra homomorphism and Riesz star homomorphism in the case of order F algebra with unit element.
Yes.
The second is what about the nilpotent element in the F algebra? And if we take the quotient with the nilpotent element, if we get some structure of semi-prime order vector pre-Riesz space.
Yeah, quotients are always a really difficult topic when it comes to pre-Riesz spaces, because there can go, like, a lot can go wrong when taking quotients. We don't even know if we have a pre-Riesz space and have a quotient by an ideal, if it's the pre-Riesz. So we don't really know much about quotients, or like there's, yeah, we've tried, but didn't really figure it out what are the right conditions to ensure that even the quotient of a pre-Riesz space by an ideal is again pre-Riesz, for example. But I haven't looked at quotients using the nilpotent elements as yeah. So maybe we get something semi-prime, but then it's not a pre-Riesz space anymore. But yeah, something like this. I don't know.
All right. Any more questions? All right. Oh,
The first question.
the first question.
Two questions about the connection between algebra homomorphism and Riesz star homomorphism
Yes.
in order F algebra.
Yeah, in general, we don't know anything about this. We don't know if an algebra homomorphism, we know that it's always disjoint preserving, but yeah, to get that it's in Riesz star homomorphism, we need some conditions in general partial order vector spaces when a positive disjoint preserving operator is again a Riesz star homomorphism, and in general that's not true, not even in a pervasive space. So the only condition we until now could find that a positive disjoint preserving operator is Riesz star is this property SD in this setting of order dense subalgebra or subspaces. And yeah, that's one of the tasks we still have to do to find a condition in a general pre-Riesz space or partial order vector space that ensures that positive disjoint preserving operators are again a Riesz star. Yeah, we're still working on that.
Thank you. But I think that if we have algebra homomorphism, that is maybe we can show that is Riesz star homomorphism without any extra condition. I think this because
if you know how to do it, then please let me know.
In the usual case, it's sample. We use the fact that he's semi-prime, so we get the result. But maybe for Riesz star homomorphism to get algebra homomorphism, we have we must add an extra condition. Thank you.
Okay, yeah, I mean that a Riesz star homomorphism is an algebra homomorphism follows quite easily by just extending the Riesz star homomorphism. Then we know it's a Riesz homomorphism on F algebras. There it's an algebra homomorphism, and then the restriction again is of course an algebra homomorphism, but the direction from 2 to 3 is the difficult part. Yes.
Okay. So now there's an online question. In case we have a complete norm, which particular structure do we have?
In most cases, I haven't considered norms in general. I mean, I'm not really sure what you
Oh, well.
mean.
That's all right. Eh? We don't have to have the answer to everything. Are there any more questions online? It looks fine. So thanks, Janko. That was very nice of you. And have a good
Thanks.
day. That's everyone clapping.
You too. Thanks.